All right, are we ready to go?
Yeah.
Okay, great. Well, hi everyone. My name is Brianne, and my research was on household willingness to adopt water conservation technology. So let's first start with the big picture, which is water scarcity. It's becoming a huge global problem because there are currently 1.2 billion people who face water scarcity. And as you can see on the map here, over half the world is facing at least medium water stress, which is really concerning. Now, there have been strategies to mitigate these problems in the past. Supply side management was really common a few generations ago, and even now, trying to find ways to increase the availability of water. However, it's kind of going to the wayside in the past few decades in favor of more demand side management, which is instead of finding ways to increase the availability of water, it's instead to decrease demand of water. And one major example of this is adopting conservation technology. And that is what my research focuses on. And if you see this bar graph here, the bar to the left shows what the total urban water use in California was in the year 2000. But as you can see on the bar next to it, that's what the water use would have been if all of California's buildings had adopted water conservation technology. So as you can see, it makes a considerable difference. But despite that difference, not every household is willing to adopt water conservation technology, and I really wanted to delve in and figure out why that was. So my research questions were what factors influence household willingness to adopt water conservation technology, and more colloquially, why doesn't everyone adopt water conservation technology? Like, what's stopping people? So there has been some research on this in the past, and the literature has identified 5 overarching ideas or potential factors that can influence water conservation behavior, and those are public opinion, cost, education and awareness, demographics, and the type of technology used. But as you can see here on this table, of all the literature I reviewed, there wasn't one that was able to encapsulate or consider all 5 of the factors at the same time. And that kind of surprised me just because we know water issues are not a one-factor problem or a one-factor solution. There's a lot of reasons why we use the water that we do and why we're not conserving. So I wanted to make sure that my research was able to consider all of the different factors. So the way I did this is through simulation, which turns mathematical models based on particular phenomena or social and physical factors, such as the factors I just mentioned in the previous slide, into a series of inputs that interact and generate complex outputs for explaining the interacting phenomena, as well as examining them in real-life scenarios. So I know that sounds confusing, but we're going to go through it step by step because there is a 7-step approach. Now, the first step was the formulation of that research question, so we've already gotten that. But the second step is to identify a simple theory, and that you can see in this diagram here. According to the theory of innovation diffusion, there are 3 states of adoption. The first is non-adopter, and then potential adopter, and then adopter. And individual or a household can move from one state to another, or even just bounce around from the different states based on the factors listed above. So those demographic characteristics, the building characteristics, and the external factors. Any combination of those characteristics can lead to a change or just impact the state of adoption. Now the next step in the simulation is to choose an approach. And the approach that I used was agent-based modeling because it's widely used for assessing micro behaviors within dynamic systems, and it enables scenario analysis based on changes in behaviors and decision attributes, which is exactly what I'm trying to look at with my research. So this is where it gets a little bit complicated, so bear with me here. But if you look at the diagram right here, you can see that we have our 3 states of adoption. And in order to get from non-adopter to adopter, we have 2 phases of transition there. So to go through the first transition, from non-adopter to potential adopter, we have an adoption, it's based on the adoption utility. And the utility is a value that is generated from the table on the right. It basically encapsulates all the different demographic and household characteristics based on a specific value or coefficient. Now the coefficient is based on the literature review on which factors are kind of the most important in impacting the adoption of water conservation technology. So for example, we have education, the literature stated that someone with an advanced degree would be more likely to adopt water conservation technology, and therefore their coefficient is higher than someone with just a high school diploma. So that's where the coefficients come from. And the summation of those coefficients and the combination of those based on those variables create that adoption value. And if that adoption value is greater than or equal to a utility threshold that the user of the model chooses, then the non-adopter will transition to potential adopter. Now what this threshold is it dictates a matter of sensitivity. So the higher the threshold is, the higher those demographic characteristics such as education, income, and the other factors have to be in order to adopt. So conversely, the lower the threshold is, the lower the importance of those factors are. So using this threshold and being able to change the threshold as the user of the model helps us to identify and target specific community profiles, since it's based on those demographic and household characteristics. Now, moving to the second transition, it's very similar to the framework of the first, moving from potential adopter to adopter. It's not based on an adoption utility, though. It's based on an aspiration index, which is more focused on cost effectiveness. So if that cost effectiveness is greater than or equal to the aspiration threshold, which again is based on the user of the model, then that second transition will be made from potential adopter to adopter. Now, a little bit more about what went into the model in order to make it run. We used 300 households in Miami Beach that were dispersed over 3 different zip codes with 3 different demographic, profiles that we looked into based on census data. And what was great is that the city of Miami Beach also provided water use data for each of those 300 households. That was also incorporated in order to give us a diverse look into the scope of the different households. And it also helps us with looking at those different community profiles. Now, the span of the research was over 20 years, so that is what the simulation will be projecting after 20 years, what changes will be made in these households and their adoption states. Now, if you look at the table on the right, we can also see the list of different technology that could be adopted, as well as their costs and their expected water savings. So this is actually what the interface of the model looks like. On the left-hand side, you see all of the different inputs that could be changed by the user to get a set of outputs that are on the right-hand side. Now, the inputs were the water price scenario. We had 3 different price scenarios that could be chosen. The rebate status, so whether there was a rebate available to use or not. Income growth, household growth, utility threshold, and the aspiration index threshold. Now, as the user of the model, I can make any combination of those 6 factors or those 6 input parameters as I want, and that's going to generate the outputs that you see on the right-hand side. Now, the outputs are the distribution state of the adoption state, the number of technologies and how many technologies were adopted, the total number of adopters, and the overall demand reduction. So here's a look at the results. As you can see, income growth had a really big effect on our adoption state. The big graph that's in the center of the page here shows that as there was an increase in income growth, you also saw an increase in the percent adopter, and this is regardless of the water use scenario or the rebate status. But what's really interesting to look at is, although there is an increase, you can see that under the fixed charge scenario, which just means that there's a fixed price, no matter how much water you're using, you're going to pay the same amount. In that scenario, there is an increase. However, it's not linear like the other scenarios. There's more of a tipping point. There's a slight increase at the beginning, but as soon as that income growth hits positive numbers, it jumps up exponentially. And you can see that trend follow through with the graph on the right-hand side too, with the number of technology adopted. So again, as the income growth increased, the number of technology adopted increased as well. So after we ran through the model, we put those results into a CART analysis, which stands for classification and regression tree. And it's basically a tree-like structure that identifies all the possible pathways leading to a specific output. So the table you're seeing now shows all of those pathways called nodes, and those nodes whose combination of input parameters led to at least a 50% adoption rate. So of all the different combinations of input parameters, these are the ones that led to at least 50% adoption. So we're going to talk about a couple of them now. If you look at node number 10, it's under the fixed price scenario. It shows that if there was greater than 4.5% increase, then the percent adopter will be 68%, regardless of the utility and aspiration index thresholds. Now, I found that really interesting because the income growth is just so high over the 20 years that it basically overshadows the importance of the utility and the aspiration index thresholds in this particular scenario, because that doesn't mean that the utility and aspiration index thresholds aren't important, because if you look at node number 35, where there is an income decline of 2%, you would expect in that case there'd be a large decrease in the percent adopters as well. But because that utility threshold is lower, which means, again, the sensitivity or the importance of those demographic and household factors is lower, we still get to see that 50% adoption rate. Now, what this research showed me, and what it can hopefully show others, is that because we were able to look at different community profiles using the different thresholds, different water planners or policymakers can strategically plan which or implement which water price structures would be best for their communities in adopting water conservation technology. So they can see maybe in a more affluent area or in a poor area or with different demographics which pricing will be best. And it also looks at different cost effectiveness of the technologies as well for possible incentives put on by the policymakers. Now, there were some limitations to this research. Our model, unfortunately, only had one dynamic component. The rest of it was all static, which basically means that we were not able to change the input parameters partway through that 20-year research span. And then in addition to that, it's important to note that agent-based modeling is a tool for exploration, not prediction. We're not trying to predict the future here. We're just exploring different patterns and trends that already exist. And then we also, unfortunately, were not able to look into social network effects or peer effects, which may have had an impact on our results. Now, for future research, I definitely recommend that more work can be done in creating a more all-encompassing utility threshold where other demographic characteristics can be considered, such as religious identity, sexual orientation, or even the number of children in the household. And that was my presentation. Thanks.